Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this lesson, we'll be looking at an example that is going to be a stripper. And again, we have our same summary of formulas, so we can calculate the height of a transfer unit, depending on whether we have film coefficients or overall mass transfer coefficients, and the number of transfer units that are appropriate for our given information. And these formulas are shown here. Since this problem will be one for stripping or desorption, just remember that some of the key things you need to know is that point of view is that the material is being removed from the liquid and being added to a clean gas. And so typically you're going to know the liquid flow rate, the composition of the liquid at the inlet and the outlet, and the gas feed composition. We can find pinch points to estimate what the minimum gas flow rate needs to be, use that to estimate the appropriate gas flow rate, and our driving force typically will be the X composition change. So in this example, we have water that contains 6 parts per million trichloroethylene. Since that's a mouthful, we'll write TCE. And this is to be purified by stripping with air at 20 degrees C. The product needs to contain less than 4.5 part per billion TCE to meet emission standards, and we want to calculate the minimum air rate in standard cubic meters of air per cubic meter of water, and the number of transfer units if the air rate is 1.5 times the minimum rate. Now I'm not going to work these others, but you could try these on your own. And we have data given for Henry's law coefficient for TCE in water is 0.0075 cubic meters times atmospheres per mole, and we know the molecular weight of TCE is 131.4. Now this is the Henry's law constant is going to tell us our equilibrium equation, so we're wanting to find y equals mx at equilibrium, and so we're going to do that based on Henry's law. And unfortunately, our units, I need these to be to mole fraction, so I'm going to also need to do some conversion here by multiplying by the density of my liquid. And so in this case, 0.075 cubic meter atmosphere per mole. My pressure is 1 atmosphere. The density is 10 to the 6th moles of water per 18 cubic meters, and then times X. So what I end up with is, in terms of mole fractions, Y is equal to 417X. So next we need to figure out exactly what my compositions are at the inlet and the outlet. If we assume a basis of 1 mole of liquid feed, it'll just make things easier. Then X coming in, based on what they said in the problem statement, was 6 times 10 to the minus 6 grams of TCE per gram of water. And I need these to be in mole fractions, so molecular weight of water is 18 and of TCE is 131.4. And so multiplying by 18, dividing by 131.4, I get 8.23 times 10 to the minus 7 moles of TCE per mole. And because these are small numbers, per mole of water is about the same as being per mole of the total. And Y star, which is going to be also the Y at the minimum gas flow rate, is going to be found using our equilibrium relationship, 417X. So in this case, it's going to be at the inlet 3.43 times 10 to the minus 7th moles of TCE per mole. Now, the liquid coming out, they told us needs to be no more than 4.5 part per billion. So 4.5 times 10 to the minus 9th, again, because this was given to us for a liquid in parts per billion, traditionally that's going to be in mass fraction, so therefore converting this to mole fraction, I end up with this. Subtracting from my X at the inlet and the outlet, I find that 8.214 times 10 to the minus 7th moles of TCE have to be removed. Now that allows me to calculate, using that and this together, I can then find the minimum flow rate. So V minimum is going to be 8.214 times 10 to the minus 7th moles of TCE divided by 3.43 times 10 to the minus 7th moles of TCE per mole of gas. Therefore, I end up with 0.002395 moles of vapor feed. Okay. Now, on a volumetric basis, if I take the 0.002395 moles of gas and divide it by my mole of liquid, for the gas, 0.0224 standard cubic meters is a mole of gas. And for my liquid, it's water, and so a mole of water is 18 cubic meters of water, roughly. And so I get about 3 standard cubic meters of air per cubic meter of water at the minimum. Now I can also do this on a mass basis. We can take that same starting ratio, and using 18 grams of water per mole of water, 29 grams of air per mole of air, I get 3.86 times 10 to the minus 3 grams of air per gram of water at the minimum, or probably more normally we would say kilograms of air per kilogram of water. So this is the minimum, and if we say that we're going to use V is equal to 1.5 times the minimum V, then we end up with 0.003595 moles of air per mole of water. Now, we still have the same Xn, we still have the same Yn, we have the same number of moles of TCE removed. What's going to change is Y at the exit. I'm going to switch to a clean piece of paper. And so Y coming out is going to be the moles removed over the gas flow rate, which is, in this case, 0.00002286 moles of TCE per mole of gas. And I need X star based on this, okay? This is Y coming out over 417 using my equilibrium relationship. So 5.48 times 10 to the minus 7th. Now I just calculate my values. So the NOx is going to be Xn, which is 8.23 times 10 to the minus 7th, minus X out, which is 6.164 times 10 to the minus 10th, all over my delta X log mean. Okay, so let's come over to the side here. Delta X log mean is going to be Xn minus X star when I came in, minus X out minus X star when I came out. But that one's 0. X coming in was the 8.23 times 10 to the minus 7th. Xn coming out is this number here. X coming out is the 6.164, so this goes here, this goes here, this goes here. And then I'm going to divide by the natural log of using the same values in there. And so therefore this answer is 4.48 times 10 to the minus 8th. And when you do this, you end up with NOx is equal to 18.34. So I'm going to need 18 and a third transfer units for this problem. So you can go back and try this for different values of V, okay, and see what the effect is on the number of transfer units. When we come back to class next time, we will look at one where I cannot assume a linear relationship for equilibrium. Thank you very much for your time.